So this is problem 2.24 out of Griffiths, which requires us to do 2.16. So the problem we're actually trying to solve is 2.24, which wants us to find the potential difference between a point on the axis, so right at the center, and a point on the outer cylinder. So that is figure 2.26, and if we look at problem 2.16, a long coaxial cable carries uniform volume charge density ρ in the inner cylinder with radius a, and uniform surface charge density on the outer cylinder shell radius b. The surface charge is negative and is of just the right magnitude that the cable as a whole is electrically neutral. Find the electric field in each of the three regions: inside the inner cylinder, between the cylinders, and outside the cable. Okay? We are not going to plot it, that's not really necessary, and I try to draw a Gaussian surface on this blown up image. So you can see I have a green Gaussian surface, which is inside, a orange Gaussian surface, which is in between, and a blue Gaussian surface, which is outside. So I guess we'll do the E fields depending on the color. So for S less than A, I'm doing green, that's the Gaussian surface we're using. And we do Gauss's law here. I'll go a little slow on these at first. So when we do Gauss's law, we're going to get the magnitude of our E field as usual. And then for that surface area, we'll get 2 pi ls. And that's equal to Q enclosed over epsilon naught. And as usual, the biggest problem here is trying to find the enclosed charge. So I'm going to do that over here. Your enclosed charge is going to be the integral of rho d tau, where d tau you could think of as being dv if you prefer. The book uses d tau, so that's what I'll use, but I guess they didn't want them to get confused with something else. But rho has units of charge per volume, and you're multiplying that by a volume element. So the units make sense. Now this is a volume integral, so we have to do a triple integral, rho, and then we need to know d tau for cylindrical coordinates. This obviously has cylindrical symmetry, we can see that. If it didn't have any symmetry, then we wouldn't be using Gauss's law, but it does, and it clearly has cylindrical. So our d tau is s ds d phi dz. So this is our d tau, and now we need our bounds of integration. So we're going to be integrating for the z component 0 to L. In other words, we're going to go the length that we need to enclose our cylinder. The phi will be 0 to 2 pi. That'll essentially always be the case. And then we will be integrating from 0 to our Gaussian surface S. Sometimes they use prime notation here, but as long as you understand what's going on, it doesn't really matter. Now, if we integrate the dz portion, first off, rho will factor out. If we integrate the dz portion, we're just going to get L. If we integrate the phi portion, we're going to get 2 pi. And the integral from 0 to s, s prime, ds prime, that's an easy power rule. You just add 1 to get 1/2 s squared. So Q enclosed is rho times L times 2 pi times s squared all over 2. And now we can say then that the magnitude of your E field times 2 pi ls is equal to rho L, I'll put the 2 here, pi s squared over 2 epsilon naught. We can see this 2 will cancel, this pi will cancel, this L will cancel, one of these S's cancel. And then the E field, we're going to drop the magnitude and add a unit vector at the end here, is just rho S over 2 epsilon naught in the S hat direction. So that's our E field for that portion of the cylinder. Again, that's inside that area. Now, if we want in between the 2 cylinders, we're going to use the orange Gaussian surface. You can see that's between them. So this will be for A less than S less than B, just saying that we're in between them. I'm not going to do the left-hand side of the integral. We're going to still get the magnitude of E times 2 pi ls equal to Q enclosed over epsilon naught. I don't think the left side is really a secret. As with most Gaussian surfaces or Gaussian problems, the real trick is to find your Q enclosed. Now it again will be a triple integral from 0 to L, from 0 to 2 pi, and then we're actually going to go 0 to A. And the reason why we're doing that is because there's no actual charge inside of this middle area. So right here, there's no charge. So there's no need to integrate to some point in between there. We only have to integrate to this A point right here, because once we do that, we're encompassing all of the charge. So hopefully that makes sense on why that bound is the way it is. We have rho, and then our volume element, S, ds, d phi dz. And again, the bounds for z and phi don't change. So the big trick there is to know the difference for the bounds. So you'll still get your 2 pi, your L, basically the exact same thing, only it's a 1/2 a squared now, which does change it. So the magnitude of E times 2 pi ls is equal to 2 pi L rho a squared over 2 epsilon naught. Okay, so again, we can start canceling some of these terms. We can see the 2 pi's will drop. We can see that the L will drop. This time the L doesn't drop though, that's the big difference. And our electric field in this region will be rho a squared over 2 epsilon naught S in the S hat direction. So that is your electric field inside there, and in between those two. So there's only one more region. That was the blue region. So that's the big one encompassing the entire thing we have there. And that is for S greater than B. Now, again, we'll get the magnitude of your E field times 2 pi ls is equal to your enclosed charge over epsilon naught. This one's actually pretty easy, but you have to keep in mind that this setup they have here is neutral. And it mentions that actually in the problem, so it's kind of a reading thing. So this is the part you want to read. The whole thing is electrically neutral. What that means is the charge that you have on that surface area there and with the volume are the exact same in terms of magnitude. So the enclosed charges, you could think, cancel one another out in a way. So because of that, the enclosed charge is just 0. So your E field in this region is 0. And we actually didn't need that E field to solve this problem, but I went ahead and did it anyways because I figured it would be good practice. So that was that portion of the problem. The reason why we did that is because now it's pretty easy to find the potential. And I would say generally the rule of thumb is if it's easy to find the E field, in other words, if you can do Gauss's law, then find the E field to get the potential. So because we had that symmetry, we used Gauss's law to get the E field, and now we can find the potential. So the potential is negative the integral of E dot dl. So if we want the potential in between, which is what the problem wants, it wants the potential from a point on the axis to the outer cell, so from B to the middle. Basically, we're going to be going from B to 0. So this will be V from B minus V0, which is, you could think of as just delta V, is minus the integral. So we're going to have to break this up into pieces. We're going to go from B to A first, E dot dl, and then we'll go from A to the middle there. And the reason why we're doing that is because your E field changes between there. So because we have this change, we have to kind of break this up into different points. So as we're going from here to here, which is basically where they want the, I don't know what happened there, the potential difference, we're going from the E field in between to the E field actually inside there. So that's the big thing that changes. And we found those, so that's actually good. The DL in these cases will be just S hat ds, S hat ds. So the S hats will end up going out of our equation here, which is nice, and we'll get the ds for the integration. So our potential difference will be minus the integral B to A. And I'm going to go ahead and just factor out our constants. So rho A squared over 2 epsilon naught. The integral from B to A, 1 over S ds, minus 1 over rho, 2 epsilon naught. The integral from A to that centerpiece, S ds. So this will be equal to minus rho A squared over 2 epsilon naught, the natural log of A over B. And then if we integrate this, it'll be 1/2 S evaluated from 0 to A. So it'll be 0 minus a minus, so that turns positive. A squared. And this will actually turn into a 4 because this is a 1 plus 1 is 2, so we'll divide that. And then we're going to do just one step of simplification. So this will just flip by using our log properties that can go in there as to the exponent, and we'll be able to factor out rho over A squared, 2 epsilon naught. You'll get the natural log of B over A because that made it positive, plus we're left with a 1/2 from the other term. And this is your change of potential. So again, just like the last problem, we had to find the E field using Gauss's law, and then from that we could find the potential. So it's kind of nice because it's working two ideas at once.